remember that we can find the change in potential energy in moving from point A to point B, under a conservative force, of course, as delta U is the integral from A to B of F dot ds. That is, we have some little path. We have two points, A and B, and there's some path. We parameterize on that path as ds, and we say at any given point there's a force, and we integrate up the force dotted into that product. All right, F ds cos theta. And of course, we can connect the force to the electric field by saying the force felt is the charge times the field, F equals QE. But we've also defined potential as U over Q. Allowing us to put all of this together, say that delta V must be the integral from A to B of E dot ds. And that's a lot of verbiage to say something which is relatively obvious, which is that the electric potential is related to the electric field the way that the electric energy is related to the electric force. All right, all we're doing, again, remember, is abstracting out one of the charges. And then likewise, with reasoning that we had used under energy, we could also turn this around to say that E is minus dV dx. That is, given a potential graph as a function of x, the electric field is the negative of the slope. We should be really careful here. We're in one dimension when we do this. All right, this is a single dimensional thing. There's only one way for the particle to move, one axis it can move along, so that the math is relatively simple. In 3 space, if we had things moving in multiple spaces, we need to use something called the gradient. The gradient is the 3-dimensional equivalent of a derivative. And so we would end up with people who have taken the vector calculus class. You'd find the electric field as a vector is minus the gradient of the potential function. On the other hand, the 3-dimensional nature is not a topic for AP Physics C. Let's walk through a few calculations to see how we might use this. Let's find the potential for parallel plate capacitors. Remember, a parallel plate capacitor, which is clearly just 2 plates that are, we hope, parallel, and they have some surface charge sigma, the other one having minus sigma on it. And we found through direct integration earlier, and then really through Gauss's law, that inside there's an electric field which is constant, going from the positive and negative plate, of course, and having a well-defined electric field strength, which is just the charge density over the permittivity constant, or sigma over epsilon naught. Since the field is constant, the integral is really, really simple, because we're saying that delta V, remember, is minus the integral of E dot ds. So if we're going to go from, let's say, let's call this x equals 0, and this would be the displacement. Let's call it d, the separation of the plates. And we're going to say we go from somewhere, from some initial position, xi, to some final position, xf. And E dot ds in this case is going to be just E ds, because they're aligned. So we get just that. It's minus E delta x. Getting back to what we said before, which is that delta V is E, that E is minus delta V of delta x. So in this case, it's really easy because everything is constant. And so we can figure out a relatively simplified form for the voltage as a function of the distance s from the positive plate, which is just sigma s over epsilon naught. Customary to define the distance actually as s equals 0 being the negative plate, so that the positive plate is at higher potential, at some higher positive potential. We can use this simple potential to explore ways that we can visualize potential, and there are 4 common visualizations. We can have a potential graph, i.e. just plot V as a function of s, of your location, and for us, 0 at the negative plate, and then growing to the positive plate. You also could draw it as what are called equipotential surfaces. In other words, places on which the potential is all the same. Notice that our potential depends only on how far we are from the plate, not on, if we were to sort of do this reference frame, think of it as x, y, and z, then only x matters. So on sheets of constant x, it doesn't matter what your Y or Z are, so they're all the same potential. So we might have half a volt potential here, and 1 volt here, and 1.5 at the other plate. And here, these equipotential surfaces, fancy word for saying a surface along which the potential is all the same, are just sheets. That's only two methods. The other two methods are what we call a contour map, where we just put out lines corresponding to the value of the potential, so it's constant along here, in the same way that you might turn a topographical map into a contour map. Or what's called an elevation graph, which is just a three-dimensional version of a graph where we let x, v vary in 2 dimensions and see what comes out, where the height of it is the potential we want. This one over here, by the way, we'll loop back to this one a lot. This is what we call an isoline picture, or an isoline picture, I guess, usually. A set of isolines where, because we represent the slice through the equipotential surface as a line on a contour map. So contour map and isoline map are basically the same. All right, 2 protons, one after the other, are launched from point 1 with the same speed. They follow the trajectory shown. What can we say about the speeds at point 2 or 3? Well, they've fallen through the same potential, right? They have the same delta V, and the change in U is just Q delta V, so they're the same change in energy, so the same delta K. But if they start at the same speed and they have the same delta K, then they must end with the same speeds as well. All right, of course, not everything is a parallel capacitor, so it's not always going to be easy. Here we'll do an example of getting the potential of a single point particle. We start with our electric field, and we're going to say that we're going from, right, we have some charge Q, we have some other, well, and we want to talk about moving from, say, this point all the way out to infinity. So distance of r out to a distance that's infinite, and we'd like to get the potential as a function of that r. So we can see our electric field, which we know is, right, we know the electric field. We can see the step ds is in the same direction, so their dot product is just 1 over 4 pi epsilon q over x squared dx, because we know the Coulomb field. And then we have over here that the change, should have written that out, that delta V is, of course, my final minus my initial, so my potential at infinity minus my potential at the point r. And that is going to be the integral of E dot ds, which is this mess here on the right. Of course, we have to find our potential as 0 somewhere, and we usually would say for a point particle infinitely far away. If two things are separated by infinity, they're not interacting, so it doesn't make sense to say they have an energy with respect to each other. So we have a 0 for v infinity, and then we can do our integral. Everything here, except for the x squared, is not a function of x, and so it comes out of the integral. So we're going to integrate from r to infinity of dx over x squared. That integral is minus 1 over x, but we're going to have to evaluate from r to infinity, carrying this minus sign for a little bit. And so when we put in 1 over infinity here, we make the math people shudder, but essentially that's just 0. And we have minus v of r is this stuff times minus 1 over r, cancel the mutual minus signs. The potential at some distance r is q over 4 pi epsilon 1 over r. By the way, we had gotten the energy of a pair of point particles, so we could have divided out the charge and gotten there as well. This is really to illustrate again that we can do this calculation relatively straightforward. It is definitely a worthwhile thing to keep track of this potential, the potential of a single point particle, because ultimately everything can be made of single point particles, so this is going to be important for us. So as the ratio of the potential at point A to the potential at point B, sorry, I guess the ratio of B's potential to A's potential based on this diagram. Well, we know that the potential depends on 1 over, proportional to 1 over r. So if I am 3 times further away, I would have 1/3 as much potential, so it must be 1/3. And that's good, because if I would put a charge at that distance, at least at this distance of 1 millimeter, and we put a positive charge here, we know that it would try to move towards B. It would move away. So it needs to move down the gradient. We need it to be lesser potential at B than at A. And that's what we have. All right, what is the electric potential 1 centimeter away from a 1 nanocoulomb charge? And answer in volts. By the way, this is kind of this annoyance about physics, but the volt is the symbol for voltage, and it's also the symbol for the unit of voltage, right? So tricky bit where we're using the same letter. In print, you'll never have a problem because, again, if it's a variable, it would be italicized. If it's a unit, it will not be. So we have that the potential is 1 over 4 pi epsilon naught Q over R, which is 9.0 times 10 to the 9 Newton meter square per coulomb square, sure, times 10 to the minus 9 coulombs over 0.01 meters, and we get something like 900. And then we have 1 coulomb on the bottom. Oops. We have coulombs over coulomb squared, so we have something over coulomb, and we have newtons times meters, which is a joule. Hey, that's 900 volts, as we'd hope. Notice that in print, it's kind of awkward that this V and that V look the same. So sometimes you'll see me, at least, when I do it, I try and put little wings on the variable. Not a big deal. You don't have to do it. It's not mandated. It's just my own little thing, so I can tell the difference. By the way, 900 volts is certainly nothing to sneeze at, right? So we don't have like a lot of charge, but we're also not very far away from it. And so we get a pretty significant charge, right? That's, 100 9-volt batteries. It's 6 times, roughly, the voltage coming that you have on house lines. So it's not trivial. It's another reason why it's hard to arrange that much charge together. All right, let's visualize the potential due to a point particle. We get, of course, in the one-dimensional case, it's just a 1 over r graph, exactly as we'd expect. A little hard to draw here, but the equipotential surfaces are each spheres, because at a fixed distance of r, we all have the same potential. So they're trying to show here a series of nested spheres with little windows drawn so you can see them. And the spheres get spaced differently as you go out because of the 1 over r. That makes the contour map relatively easy. It's just a series of circles. All right. And if we were to graph it as a 2-dimensional graph, we would see it's this little thing, this little like Devil's Tower Mountain thing, where it's wanting to, of course, spike off to infinity here, right? As we get to really, really small r's, we can see the 3 circles, the 3 drawn circles. Right? You can see where those contours are coming from, which is nice. And you can also see that this is sort of what's called a pole. It looks like someone has got a tent and they've stuck a tent pole in it to hold the tent up. And because this is a single particle, we would also say that the single point particle is what's called a monopole. That word will come back to haunt us a little bit later, and so it's worth flagging out here. You don't usually hear single charges called monopoles in electricity, although you do sometimes, and it's certainly the correct notation. All right, a proton is released from rest at the surface of a 1 centimeter diameter sphere that has been charged to plus 1,000 volts. What is the charge of the sphere? All right, one really important thing to note here, which is easy to miss, it's a diameter. So this is really a radius of 0.005 meters. Also, it's a sphere. So we know that from the shell theorems, it will behave like a point particle. So even though we don't have a point particle, we can say, oh, that it's the potential of the equivalent point particle that distance away. So we take V is 1 over 4 pi epsilon naught Q over R. We invert it and say Q then must be V times 4 pi epsilon naught R, which is 1,000 volts, times 0.005 meters, and 1 over 4 pi epsilon naught is 1 over 9 times 10 to the 9 Newton meter squared per Coulomb. And so, per Coulomb, sorry, square. And if you work all of that out, you get 5.6 times 10 to the minus 10. And we have joule per Coulomb for the volts. And then this is then 1 over joules per Coulomb square. So all it turns out to be coulombs as expected. So that's our answer. All right, what is the proton speed at 1.0 centimeters from the sphere? And then we got to be careful about what do they mean by from the sphere. So here's our sphere, which has radius r, which was 1/2 centimeter. And from the sphere might mean, I think I'm taking it to mean another 1 centimeter over. So the actual distance, let's say call that capital R. Let's clean this picture up a little bit. We'll have a sphere of radius r, and I'm interpreting this as saying it is 2r further away, so that this distance is 3r. And we can say that the energies are conserved. So it starts at 0, but having some initial potential energy, which is the charge times the potential that it was on. And then that ends up with its, let's call it initial potential energy. And then we have 1/2 mv squared plus E times its final potential. So a lot of V's going on here, which is a little awkward, but we get 1/2 m little v squared is charge of the electron times the initial voltage minus the final voltage. And therefore, the actual velocity is going to be 2 times the electron charge over the mass times the difference in voltages. But if we're 3 times further out, we know the voltage is 1/3 as much. So I can say it's 2e over the mass times 1/3 the original voltage. All right. Of course, we need to actually know these values. Let's see if we can clear out some room. Not easily. All right, well, we'll go up there and do that. So the velocity is 2 times the proton charge, 1.6 times 10 to the minus 19 coulombs, over the proton mass, 1.67 times 10 to the minus 27 kilograms. These are things that are in appendices or on the equation sheet or, live in Google. So at some point, you would just have to look them up or, learn them, I suppose. Times 1,000 volts over 3. Actually, 2, because this should have been 2/3. It's V minus V0. So times that. And we end up with something like 3.57 times 10 to the 5th. And I suppose I could say on faith, I'm pretty sure it's meters per second. Let's just check it out. Coulombs per kilogram times joules per coulomb square rooted. A joule per kilogram is, a joule per kilogram. Well, a joule was kilogram meter square per second squared per kilogram. Hey, look, meters per second, yay. So 3.57 times 10 to the 5th meters per second.